Hey guys, welcome back to chapter 6 on energy and equilibrium. So let's finish off the chapter and look at those last aspects of Le Chatelier's principle for when an equilibrium system is disturbed. We've looked at adding and removing chemicals, and we said that when you add a chemical, you move equilibrium away from that chemical to try and compensate for having too much of that chemical. When you remove a chemical, equilibrium moves towards the chemical to compensate for having too little of that chemical. The system's always trying to compensate. That's what Le Chatelier's principle is telling us. Same with changes in temperature. You increase temperature, you're putting more energy into the reaction. Reactions which can compensate and use up that extra energy are endothermic reactions. Endothermic reactions take in energy. We can recognize them because the energy term looks like a starting reagent. So rises in temperature favor the endothermic reaction. You drop temperature, you're taking energy away from the chemicals. So to compensate, we need help from the reaction that produces extra energy. That's the exothermic reaction that gives energy out to its surroundings. We can recognize the exothermic reaction because the energy term looks like one of the products at the end of the reaction. So a drop in temperature favors the exothermic reaction. We said that an addition of a catalyst doesn't change the position of equilibrium because it's lowering the energy of activation for both the forward and the back reaction. So we reach equilibrium faster, but equilibrium does not change. Last thing we need to look at is changes in pressure. A change in pressure will affect any gases which are in the system, but only gases. No effect on solids, no effect on liquids or solutions, just gases. So the analogy we can use is that of a syringe. And if we imagine that the syringe is half full with air, the only picture I could get would be with the syringe all the way down. So let's say we take 2 milliliters of air in the syringe, and then we block off the end of the syringe so no gas can get out. If we were to push down on that syringe, it would pressurize the gas inside. And that gas would be forced into a smaller space. And that's the first thing we have to think about. When pressure increases, it's going to feel like a volume decrease for these chemicals. Now, to compensate for that reduced volume, Le Chatelier tells us that we favor the reaction that's producing the least moles of gas. Increased pressure, reduced amount of space, favor the reaction producing the least moles of gas. Conversely, if we start to pull the syringe out, without pulling it out all the way, mind you, we start to pull it out, like not you really need a diagram or a picture to show you, start pulling it out, the volume inside the syringe starts to increase. So a decrease in pressure as we back off causes an increase in volume. A bit like if your chemistry instructor stops pressurizing you and backs off, then you've got more space. And it's the same analogy for these chemicals. When the pressure's off, they have more space. Le Chatelier tells us that the chemicals want to instinctively fill that extra space with chemicals. So when the pressure is decreased, we favor the reaction producing the most moles of gas. Let's take a look at some examples and see that in effect. Haber process, that should be a capital for Haber. Haber process is a good example. So if we increase pressure, increasing pressure, we said favours the reaction producing the least moles of gas. Increased pressure, we're looking for the least moles. So as we look at our chemical reactions, forward reaction and the back reaction, the forward reaction takes 1 mole of nitrogen with 3 moles of hydrogen and turns it into just 2 moles. 4 turns into 2. That's producing less gas in the system if the forward reaction is favoured, and so equilibrium moves to the right. The forward reaction is indeed favoured. Conversely, we can decrease the pressure. If we decrease the pressure, it's the opposite effect, and equilibrium is going to move in the opposite direction. So that decrease in pressure favours the reaction which produces the most moles of gas. That's our mantra. Decrease pressure, we're looking for the most moles. Because the pressure is off, we've got more space to fill. That can clearly be interpreted as the back reaction from right to left, starting off with 2 moles, and we turn it into 4 moles. So the back reaction is favoured because we go from 2 to 4. That's definitely action which is producing more moles of gas. And so we say that the back reaction is now favoured. The only time pressure would have no effect would be if the forward and back reactions have equal numbers of moles of gas. Remember, it's just the gases we're looking at. If one of the reactants or products is a solid or a liquid, we don't include that in our calculation for changes in moles. Well, let's look at more examples. So our first one, increasing the pressure. We're looking for the reaction that produces the least moles of gas when we increase pressure. So we've got the phosphorus trichloride and the chlorine turning into just 1 mole of phosphorus pentachloride. Forward reaction is favoured. It produces the least moles. Increasing the pressure in reaction 2. Again, looking for the least moles of gas. We start with 3 moles of fluorine in the back reaction. Again, ignore the sulfur because it's a solid. 3 moles, and that turns into just 1 mole of sulfur hexafluoride. 3 becomes 1, back reaction favoured. Let's look at some examples of decreasing pressure. If we decrease pressure, we're looking for the reaction producing the most moles of gas. That's the forward reaction here, 4 moles of ammonia with 5 moles of oxygen, so 9 in total, becoming 4 plus 6, 10 moles. So the forward reaction increases the number of moles of gas when pressure is decreased. Finally, decreasing the pressure for our last system, we're looking for the most moles of gas in a reaction. The back reaction starts with 0. It's got 6 moles of iron oxide, but that's a solid. No gas starting off the back reaction, but it does produce iron oxide and, crucially, there's 1 mole of oxygen gas. So we go from 0 to 1 if we favour the back reaction, and that decrease in pressure will indeed favour the back reaction. Look for the reaction with the most moles of gas when pressure is decreased, because we've got more space and we want to fill it. Take a look at the next two. You can pause the video and try and answer them. Increasing pressure or decreasing pressure, the effect on the first system. And then final example, well, there's one more over the page actually, I beg your pardon. Student experimenting with dinitrogen tetroxide being converted into nitrogen dioxide. Describe 4 things that could be done to enhance the amount of nitrogen dioxide produced. This is like how Le Chatelier's principle is used in industry. We want to use Le Chatelier to trick the chemicals into producing more of a specific chemical product. How could we use Le Chatelier to make more nitrogen dioxide? And finally, over the page, this is actually one of the reactions for lab this week, which is an equilibrium lab. A forward reaction which uses up dichromate to produce chromate, CrO4. A back reaction that uses up the CrO4, the chromate, and turns it back into dichromate. Now, if we introduced sodium hydroxide to the system, how would it affect the position of equilibrium? One extra piece of information is that sodium hydroxide, which contains hydroxide ions, remember the sodium makes it water soluble and it dissociates in water. So the hydroxide from sodium hydroxide combines with hydrogen ions to produce water. And that is a very vigorous reaction, that reaction to produce water. Explain the observed change in color and a change in the equilibrium position. Okay, pause the video if you wish and take a stab at these 3 questions, all taken from previous exams in Chapter 6. Okay, I guess we're back, or people have unpaused again. If we look at this first one, so increasing pressure. Remember that increase in pressure is like a decrease in volume. So if we've got less space, less volume, the reaction is going to favor the one producing the least moles of gas. Let's take a look. The forward reaction starts with 2 moles of hydrogen. Remember, carbon is a solid, unaffected by pressure changes. Forward reaction uses up 2 moles of hydrogen and produces 1 mole of methane. 2 moles of gas becomes 1 mole. The forward reaction is decreasing the gas volume. So that increase in pressure would favor the forward reaction. Alternatively, decreasing pressure. A decrease in pressure, if you stop pressurizing someone, you back off them, you give them more space, just like giving chemicals more space. And so with more space, when pressure is decreased, you favor the reaction with the most moles of gas. And for us, that would be the back reaction, 1 mole becoming 2 moles. In the back reaction, so we say that the back reaction is favored. Remember your mantra. Increase pressure, look for the least moles of gas produced. Decrease pressure, look for the most moles of gas produced. All right, let's go to the second one. The production of nitrogen dioxide. How would we enhance our production of nitrogen dioxide? Let's go to red. So we had talked about adding chemicals to the system. Adding chemicals would make the reaction move away from that chemical. But remember that the chemical that we're trying to produce is a nitrogen dioxide. That's what we want. And so fundamentally, to get to nitrogen dioxide, we need to move from left to right. We are actually talking about methods that would favor the forward reaction. Anytime the forward reaction is favored, here we produce more nitrogen dioxide. So that's maybe an easier or more straightforward way of thinking of the question. So to move towards the NO2, we could argue that we'd move away from the N2O4. So adding N2O4 should move equilibrium to the right. There's the N2O4. Add more, we move away from it. We'd compensate for having too much by using it up to produce more of the products of the forward reaction. We could also remove a chemical. Removing chemicals moves equilibrium towards that chemical, so we could remove the NO2. Literally scoop it out of the reaction mix. That doesn't stop it being produced, because it's collisions in the forward reaction with N2O4 that produce NO2. Taking away the NO2, storing it in a separate vessel, as the reaction is ongoing, that doesn't stop the NO2 being produced. It does, however, slow down the reproduction of the N2O4. NO2 molecules collide and reform into N2O4. So by taking away the NO2, you take away the fuel of the back reaction, and the forward reaction is favored. We could also change temperature, but we need to know what kind of reaction the forward reaction is. Forward reaction starts with the N2O4, it finishes with NO2, and this energy being given out is written amongst our products. Reactions which give out energy are exothermic reactions. So now we have to remember which action favors the exothermic, increasing temperature or decreasing temperature. It is, of course, decreasing temperature. If the molecules lose energy, we compensate for that energy lost by producing more energy as the forward reaction gives energy out. Increasing temperature would favor the competing back reaction, which is the endothermic reaction. Finally, for pressure, as we look at the forward reaction, we take 1 mole and turn it into 2 moles. So we are looking for the reaction that favors the production of the most moles, 1 becoming 2 each time. And to favor the most moles, we need more space. To create more space, we need to back off the pressure. So a decrease in pressure will favor the forward reaction. Maybe that's too literal, just edging back in my chair. I'm sure you get it. You're all smart people. So there we have it. 4 things we could do. Add more N2O4, remove the NO2, decrease temperature, or decrease pressure. The one thing that wouldn't work and is often used for this answer is to add a catalyst. It works with these irreversible systems, reactions which are moving in just one direction. Chemical A plus B, whoops, that's a very funny B, turning into chemical D and F, but it's a one-way street. That would certainly benefit with a catalyst. But reversible systems lower the energy of activation for both competing reactions. So they don't change the position of equilibrium, we just reach equilibrium faster. Okay, on to the last one. So an equilibrium system is put in place. We've got Cr2O7 dichromate turning into CrO4 chromate, and the chromate turning into dichromate, back and forth. And we've reached a point of equilibrium where the dichromate turns into the chromate as quickly as the chromate turns back into the dichromate. And then we throw a fly in the ointment, the sodium hydroxide, which contains hydroxide ions. Hydroxide ions like to react with hydrogen ions. So it's a little bit like having Hell's Kitchen with Gordon Ramsay standing there, and all these cooks trying to cook things, but one person or one of the cooks takes all the fat or cooking oil. There's a finite supply. And if one person takes too much, there isn't enough for everyone else. Likewise with our supply of hydrogen in this system, these hydrogen ions. The hydrogen ions aren't just used up by the hydroxide, they're used up by the chromate in the back reaction. So if we use up the hydrogen in the equilibrium system, which is also working alongside in the speaker, it's like we just removed hydrogen ions. So this is what the hydroxide's effect is. It causes a removal of hydrogen ions. We have used them up for this much more aggressive, rigorous reaction to produce water. The system sees this, and Le Chatelier tells us that when a chemical is removed, like hydrogen ions, the system will compensate by moving towards that chemical. And so that's going to be a movement from left to right, producing more hydronium ions, or hydrogen ions actually, and also producing more of the chromate as it uses up the dichromate. That's why the orange color fades, because we're using up this chemical, and why the yellow color starts to dominate, because we're producing more of that chemical. Color is really proportional to the amount of that chemical we have in solution. So the addition of sodium hydroxide, which is not directly involved in the equilibrium system, not directly involved, it does, however, cause a common ion effect. That common ion being the hydrogen ions, which are no longer in plentiful supply, so equilibrium moves to the right to compensate for that. Never forget, equilibrium is always trying to compensate for the action that's being forced on it. Le Chatelier tells us how the system reacts. Okay, that is it for chapter 6. We are done. Remember your mantras for adding chemicals, removing chemicals, and changing temperature, changing pressure. Don't forget about your collision theory, because equilibrium is just half of the chapter. Think about the ways that we can speed up the rate of a reaction. Think about how it affects the energy of activation, the kinetic energy of the molecules, and the number of collisions, as we outline in each of those little tables after each of the 5 factors. Think about your exothermic and endothermic reactions, the energy diagrams, and how we recognize a reaction as exothermic or endothermic. Does more energy go in or come out? Is the energy of the reactants higher or lower than the energy of the products? Does the graph finish higher or lower than it started? Does the reaction give out energy or take in energy? These are all good examples of the kind of things you want to know for the Chapter 6 exam at the end of next week. Okay guys, have a good weekend, what's left of it. I'll see you all soon. Bye-bye.